Welcome to LD Talks. I am Arun. Today we are going to talk about Polar-NRZ and Polar-RZ schemes. Here is the talk outline. We are going to talk about the basics of polar encoding and compare it with the unipolar encoding technique. Then we will check the variants of several polar encoding schemes, and we will discuss about the NRZ schemes and the Polar-RZ schemes in this talk. So what is polar encoding? In the polar encoding, we are using two voltage levels, rather two symmetric voltage levels on the both side of the zero line. You can see from this diagram, here is a plus 25 volt and there is a minus 25 volt. So because of using this both voltage levels, we can reduce the baseline wandering, and we also reduce the DC component problem which we have faced in the unipolar encoding scheme. So these are the variants. In this talk we are going to cover this NRZ-L and NRZ-I, which represent the NRZ level, and NRZ-I stands for the NRZ inverted, and the RZ scheme. So in Polar-NRZ, we have already discussed that we will represent the binary 0 and 1 as positive or negative voltage, or vice versa. There are two variants we have already seen, and like the unipolar NRZ, in the Polar-NRZ also the voltage never comes to 0. It's either remains at positive voltage level or it remains in the negative voltage level. So in NRZ-L scheme, the entire scheme depends upon on the input data stream. If we get the 0 in the input data stream, may either we represent the 0 with lower voltage level, and if we get the 1 in the input data stream, we will represent as the upper or positive voltage level. So it's entirely or solely depends upon the voltage levels whatever we are encountered so far. So here is example. For say here I am getting a 0, so that's why it's a negative voltage level I have considered, and then whenever I'm getting a 1, it represents as a positive voltage, and we have maintained this pattern for the throughout the entire data stream. So there is a fundamental difference between the NRZ-L and NRZ-I scheme, that in the NRZ-L scheme, that the entire binary data is encoded into the level voltages. From the level of the voltages, the receiver will count how many zeros and how many ones in the data stream. So there is a problem. If the sender and the receiver both are not really synchronized, so then the receiver can misinterpret the result and entirely land up with some erroneous result. But in case of NRZ-I scheme, whenever we get a binary 1 in the input data stream, we will represent it as a transition in the resulting outcome, not as a level voltage. Yes, we will use the level voltage obviously, but the 1 will be counted as a transition in the system, and if we encounter any 0 in the data stream, there will be no transition. So we will see it with the example. For say this is the entire data stream, and here is our NRZ-I scheme. So here is the 0, and whenever I'm getting a 1 in the input data stream, there is a transition. It's going from up high voltage positive voltage to the negative voltage, and it remains in the negative voltage as there is two zeros followed by the 1. So and then after, again when we are getting a 1, then there is a change in state, again 1, there is a change in state, and so on. So that means in case of NRZ-L, the voltage level remain at the same level if there is a identical symbol elements. If there is a long trail of zeros or long trail of ones, the voltage level either remains at the positive or in the negative voltage level. But in case of NRZ-I scheme, the voltage level remain at the same level if there is a trailing amount of zeros. From here we can see if there is consecutive number of ones, there is an alternating pattern we will get. And the applications we have, we can see that in USB, CD, and Ethernet, I mean, we use the NRZ-I scheme. Well, this is another example. Here there's just from the previous problem. Here the convention is just opposite. I mean, we take the 0 as positive and 1 is negative, and we just derive the entire pattern. But the interesting fact is that for the both of the convention, this NRZ-I remains same, because in NRZ inverted scheme, I mean, the level voltage contributes less. I mean, what can I say? I mean, for the NRZ-I scheme, I mean, the more important thing is the transition from the positive voltage to the negative voltage, not the level voltage. The level voltage can be vary a little bit. There will be some noise or attenuation or whatever, but we will count the number of transitions. From there we can understand how many ones are in the input data stream. So here you can count, say, 1, 2, and 3, and 4, and you can find exactly 4 ones are there in the entire data stream. And you can start with any example, which start with 1 or 0, and you will get the same result. So there is some advantage and disadvantages of the Polar-NRZ scheme. As we know, the schemes are easy to implement, and by the using of voltage levels, we have discussed we have reduced the DC component issues, and due to presence of NRZ-I scheme, it's I mean, it's easier to synchronize, because in NRZ-I scheme we are not really depending upon the level voltage, rather than we are counting the transitions. So if there is any noise or something, the level voltage might change, but the number of transition will represent the number of ones. So in the receiver's end, I mean, the receiver can easily count the number of transitions. From there, the 0 and number of ones will be clear in the input data stream, and the receiver can regenerate the data again. And there is some drawbacks of the Polar-NRZ scheme. We know there is some amount of baseline monitoring still persists, as we discussed in the NRZ-L scheme, because it's solely rely on the level voltage mechanism, and there is a synchronization problem for the very long consecutive number of zeros or ones, because we have seen in the NRZ-L scheme, if there is a trailing of zeros and trailing of ones, so the level voltage remain at the same level. So if there is any error, the receiver can't understand that whether that 1 or 0 just resulted because of the error, or it's in the data pattern. In case of NRZ-I scheme, we have seen that if we put the number of a very large number of 0 in between somewhere in the data stream, the input I mean the output waveform level will remain at the same level, but only we can handle the any large number of ones for the NRZ-I scheme, where we can see the alternating patterns in the entire system. So these are the assignments. Here we can think about this NRZ-L and NRZ-I scheme for this pattern, and as we have discussed in the unipolar coding, and we have shown that how to write the mathematical expression for these waveforms. I expect here you can write the mathematical expressions for the NRZ-L and NRZ-I scheme. And the third problem is a little bit interesting, that in the NRZ-I scheme we have seen that if there is 1, there is a transition. We are just thinking about the just reverse of that. If there is 0, we will think about the transition. If there is 1, there is no transition. Then what the change we will see in the entire system. So now come to the point where we will discuss about the Polar-NRZ scheme. I mean, in Polar-NRZ, the waveform not changing between the bits, but so during each of the bit, the entire waveform comes down to 0, as we know for the return to 0 scheme. So as the previous polar schemes we have discussed, there's a 3 voltage, 0, positive and negative. So, and in the RZ scheme, we know only the first half within the bit period it represents the data, and the next half is is a transition towards the 0, and then after either it's go below the 0 line or it's go above the 0 line, depending upon whatever the bits we are encountering. So at just 0 and 1, here also we represent as a positive or a negative voltage or vice versa. And here the 0th level is just acting as a resulting level. It's I mean, for each of the bit the waveform comes down to 0, but goes on the next starting of the period either above of the line or the down of the line. So it's just a resulting state for each bit for the t/2 to t. I mean, if we think that t is the bit period. So here from the example, it's quite clear that here we have taken the data as 1. There's a clock pulse, so it's 1. It's representing 1 here, and it comes down to 0. Then it remains 0 for the later half part of the bit period. Then again, as there is a 0, we go towards the negative voltage level and remains at the negative voltage level up to t/2 time limit. Then again it's come to 0 and remain for the rest of the part. And if we just check the entire scheme and we get this waveform, or just start with an example. Say here this is the term. Let's say just a minute. Okay, so here this is 1 and here this is 0, right? So the thing is okay, so from here we can see this part, only this first part, I mean it's the first half just represent the 1, and then after it goes down and it remains at 0 for this part, and then again it goes to 0 and then again it goes to 1, right? So these are the resting state, right? This R for say RS, resting state. So this is the resting state here. So, and if you check this prescription for the rest of the bit patterns, for say that whenever we are getting 1, this NRZ-L style of data, then we can see from 0 it goes to 1, then again it's going towards to 0, then again it comes to 1, and then it comes to 1. That means this is the positive voltage and this is the negative voltage. So it's a positive voltage level for the 3 ones, and then again there is a transition for this provides a little bit of ease to synchronization, because if there is a trailing number of zeros and ones, no matter what, for each of the bit it have to come to 0, and that's why there is a change for each of the bit, I mean during each of the bit. So there is also some pros and cons of the Polar-NRZ scheme. It solves the problem of synchronization of the NRZ as we have discussed, and it reduces the DC component. And there is some cons also carries with this Polar-NRZ scheme. It requires 2 signals to change the encoder bit, so it occupies a greater bandwidth, because it's clearly visible that due to RZ mechanism, for each beat the resulting waveform have to come to 0, no matter what, whether it's in the positive voltage level or in the negative voltage level. So, and there is a sudden change in polarity interpreted as once, as it might seems that due to sudden change in polarity, the all ones are remain as ones, uh, the I mean it's really problematic to find out the erroneous ones and whatever the real ones in the system. I mean, maybe due to change in the polarity, the 0 becomes the 1 and the 1 remains in the 1. So it's really problematic to find the exact bit patterns. So, and as we have said, it requires a greater bandwidth. So hope we have cleared the basics idea of the NRZ-L NRZ-I scheme. So if you haven't seen the previous lectures on unipolar encoding schemes, I will suggest you go back and watch those lectures and address these assignments for the better understanding. Hope you have enjoyed the lecture. Thank you.